Welcome back to Math 30-3. We're on Unit E right now, Applications of Exponents and Logarithms. So you completed your Unit D, which was, if we look at our standards, so this is the ED standard, so demonstrating understanding of logs and laws of logarithms. We completed, and then we kind of did a little bit of these ones too. We did some solving, but basically with common bases. So now specific outcome 5 and 6 we're going to tackle. So solving problems that involve exponential equations and then representing data using those functions to solve problems. So starting off on the standards for this unit, or sorry, for this lesson, we're going to be doing these types of questions. So if you need to pause this and just have a look-see at that. And this is just from the standards that is on the Google Classroom here. Okay, so for the overview, we're going to learn to solve exponential and logarithmic equations. And so solving the equations, okay, and then applying them to real problems. So we've talked about exponential growth and decay, but now we're going to compound interest, loans, half-life, etc. And we're also going to get into, so these were introduced logarithmic scales, but we're going to get into them. So first off, just to review how we would solve something with a common base. So we would, given this question right here, we would need to write this as 2 to the power of 6, okay? And then we would be able to get rid of the bases and equate the exponents, okay? This one right here, so I would just need to put this is 2 is going to be 2 to the power of 2, so then I'd have 2 to the power of 2x is 2x plus 3, so I can get rid of the powers and I equate the exponents, and I would subtract 1 x right there, so I'd have x is equal to 3. Okay. All right, so we also looked at examples when we didn't have a common base. So there was 2 ways we did that. We would convert it into a log, or we could also use it, the graphing calculator, and just use the intersection. So like y1, y2. Okay, so explain why this solution cannot be determined by converting to a common base. 50 can't be written, cannot be written as a base of 2. Okay, so the closest would actually be between, so 2 to the 5 is 32, 2 to the 6 is 64, as we just reviewed. So it would be somewhere in between those two. So determine by considering powers the 2 integers between which the solution must lie. Okay, well, the solution must be between x and 5. Okay, so this is saying that x has to be greater than 5, but less than 6. Okay, using the intersection feature of your calculator. Okay, solve. Okay, well, so this, you're doing y1, y2. Okay, y2 is going to be that line right there. So y is equal to 50. And then your doubling, okay, is going to go up like that. So there's my 5 and there's my 6. 1, 2, 3, 4, 5. There's 6 right there. So it's going to be somewhere up in there. Okay, so that's what it's going to look like, but we need to actually go into our graph. And so clear, and so we want the 2 raised to the power of x, and then we want 50 graph, and we might have to change our windows here, I'm guessing. Yep, so I go to window, so my x min, I would just go 0. My x max, I would go 10, okay, because I know that it's going to be maxed out there. And then I would go to 70 here for my y min. I'm going to put 0. Y max is going to be 70. And then this graph should look really similar. Okay, and then I've got my 50 coming across. So then I just need to find that intersection right there. So intersect 5. Okay, and then I go enter, enter, enter. So it is going to be 5.6. Okay, so x is equal to 5.6, and I rounded at the 10th. Okay, so 2 to the power of x equals 50 can be solved also by taking the log of both sides. Okay, so you can do anything you want to an equation as long as you do it to both sides. So by doing this, we can then utilize the power law, okay, the power law for the logarithm, okay, and then in order to simplify this, we would divide both sides by log 2. So I'd have x is equal to log 50 divided by log 2, which then I would just substitute into here. So quit, clear. So these are both the common logs, right? So then I would have my log 50 divided by log 2. Hopefully this does the, yeah, okay, good. I wasn't sure if I was gonna need to put brackets around there, but there's my 5.6. Okay, and then the equation can be solved by converting to a logarithmic. So that's the way we did in unit D, okay? So we know if I've got like 2x is equal to 50. So remember that the base of the exponent is gonna be the base of the log, okay? Oh, this is supposed to be a 50. And then the value right there is gonna be the argument, and then that's going to be what it's equal to. Okay, and so then if I plug that in, I would get the 5.6. This calculator, of course, can't do it directly, but then I would just use my change of base formula that states I would have the log of my argument on top and the log of my base below. So that's how I remember base below. This base goes below, and then of course I would have 5.6. So you've got 4 different ways of solving this now. This is the newest one, okay? Those ones we had talked about before, okay? So let's talk more about this solving exponential equations algebraically. So first thing you need to do is, if it can be written as a common base, it is definitely easier to do that. Okay, if you can't, then you would do the either converting the exponential to logarithm and then solving, or you would take the log of both sides and then solve. Okay, and so this is just saying you can use natural log for both of those, but I mean, kind of, why would you? You're just going to use the common log. Okay. So if 2 quantities are equal, then the log of the 2 quantities are also equal. That's how we can just take the log of both sides, okay? And then each of the methods in this point have their both strengths. It kind of depends on the exponential equation being solved. More complex ones, I would just do the base 10 each side, but you need to know how to do both of them, okay? So the graphing calculator, you can either do the intersection method like we just did, y1 is equal to y2, and find it, or you could use the 0 method, which, like, of course you can do, but it just means you have to rearrange the formula a little bit. So if I go back to here, it just means if I wanted to use the 0 method, so it would be 2x minus 50 is equal to y. So you would just do that, you'd plug that in, and then you would just use the 0 feature, okay? So it's kind of, I think it's kind of an extra step. It's not really like necessary. If you know how to intersect, then you're good, but you could do that way. Okay, so this one, it says, solve the following equations expressing the solution. So either as an exact value in the form of 1 log over the other, or to 3 decimal places. Okay, so this one right here, let's just do our new way of doing this. Okay, so log 4x is equal to log 12. Okay, and then I use my power rule, log 12, and then I'm going to divide by the log 4, log 12 over log 4. Okay, so that's my exact value in that form. So that one's done. So that's, I'll just go like this. And then in order to get my 3 decimal places, I just literally have to put it into the calculator. So log of 12 divided by log of 4. So 1.8, 3 decimal places, 1.792. 1.792. Okay. All right, let's do this next one. So the first thing I'm gonna do, I'm gonna move that over because I want all my constants together. So that's gonna give me 36. Then I'm gonna take the log of both sides. Log 8x is equal to log 36. I'm gonna use my power law. So x is equal to log 8, oopsies, not equal to, multiplied by log 36. And then I'm gonna divide, which I'm gonna do up here. So x is equal to log 8 over log 36. So that's my first part of my question. And then my second part, I am just plugging it in. Log 8 divided by log 36. So x is equal to 0.580. Okay. Okay, yeah, I knew I did something wrong. That's why I paused. Right here, this should be the other way. I'm like, why? There we go. That's okay, it happens. And it happens because I didn't show my work here. I divided by log 8, which means it's gonna be on the bottom. So then it's gonna be the inverse of this. So I could just take my answer, second answer, and then take the inverse, so like raise it to a -1 kind of thing. So my answer is gonna be x is equal to 1.723. And then just to make sure, I'm just gonna do the whole thing again, divided by log 8. There we go, and there's the 1.72. Okay, show your work so you can see your mistakes. All right, now we've got a word problem. According to Stats Canada, in the 21st century, Canada's population has been growing at an average rate of 1%. So that's where this comes from right here. That's basically saying like the 100%, and then we're adding 1%, which is gonna be 101%, which then when we write it as a decimal, okay, will be 1.01. If it was declining by 1%, then it would be 0.99 because we would take away the 1 from the 100. Okay, so we've got our formula right here. Can be used to predict the population n years after the known population. So that's going to be n naught. So anytime you've got a little 0 there, it's red is not. Okay, if the Canadian population at the beginning of 2001 was approximately 30 million, estimate the year in which Canadian population will reach 50 million, assuming the same average annual rate. Okay, so this is, P is predicting it after so many years, so it's gonna be 50 million. Okay, and it's gonna be equal to that 30 million is our starting point, and then 1.019, or sorry, 1.01, I said 9 because I was reading N. And then I would y1, y2 this, because it doesn't say I have to do this. y1 is equal to y2. Okay, and we could simplify this down. Like if it's million on both sides, okay, I could just simplify this by doing that. Okay, I just took out the 10 million. Okay, so you can y1, y2 this. So let's do that. So, oopsies, clear, y1, so clear, so I want 5, and I want 3 times 1.01 raised to the power of x, and then there's my line of 5, so I'm gonna adjust my, well, that's weird. Let's just look back at my, looks like a straight line. Oh, that looks okay. I think it's just the windows then. So I know that my y, I only need to go up to 5, and I've got it going up to 70. So I'll just do that. And let's see. Oh, what's going on here? Raise to the, oh. Okay. Let's see. I think I just need my window. So my y max, let's do, well, I guess we're talking about like almost doubling the population. So it's probably gonna be, I'm gonna put 100 for x max, and then I'm just gonna make sure 3 times, yeah, that looks good. Okay, graph. There, that's better, that's better. Okay, so then that's my intersection point that I'm gonna find. So then I go calc intersection, and then that's going to be, so 51.33. So intersects at 5 and 51.338. Okay, so then this is at the beginning of 2001. Okay, so after, so 51, and we're gonna need 52. Okay, so we'll reach 50 million. So it'll be after the 52nd year. So at the beginning of 2001, so at the end of 2001 will be 1 year. Okay, so then therefore at 2052, at the end of 2052, you'll have 50 million peeps. Okay. All right, so then you can do 1 to 4. Maybe just do like the, if there's like, yeah, like just do half of them or something like that, like the left-hand column. Okay, and then let's talk about exponential equations that are more complex. All right, we're back. Okay, we're doing the second part here. So solving exponential equations, which are more complex, okay? So in the form of like say like bx plus c is equal to d, and let's go ex plus f, something like that, okay? So we've got a whole lot going on here. So can't necessarily, you could solve them with common bases, but we're going to be given examples that you can't. So the equation, for example, here, the 6 and the 3, we cannot write them as the same base. Okay, so we would take the log of each side and then solve. Okay, and once again, you can use natural logs, but why would you just use base? So here we go. We took the log of both sides. Okay, we use the power law, okay, and to put out front. And then if you look here, I distributed, or they distributed, okay, so distribute the 2x and the -1, okay? Now we want to gather the x's together, okay? Gather the x's. So that's why this got subtracted over here. Okay, now we want to get the x's by itself. So you're gonna factor out the x, factor the x out, and then all you have to do is divide. So we've got negative log 3 all over 3 log 6 minus 2 log 3. Okay. And then this, like, we could probably gather this up as a single log, but for now this is what you would have, okay? And then an approximation to the nearest tenth. So I'm just gonna write this up again right here, negative log 3. And then just to make my own life, well, nah, I'll just leave it. I was gonna use the power law, but okay, so you just have to plug this in, and you probably wanna make sure that you are using your brackets, okay? So we've got negative log 3, okay, and then that's going to be divided by, and then I'm going to put this in brackets, 3 log 6 minus 2 log 3, okay, and I get negative 0, so it's to the nearest tenth, 3, okay. Okay, so yeah, and if you wanted to make sure that is there a next one with, okay, I was gonna say you could always y1, y2 that, to make sure, like, do your y1, y2, and find the intersection just to make sure that you've got that value. All right, last example here. So the solution to this equation, it's telling us it can be written like this. So it says evaluate the solution to 2 decimal places. Okay, so we're just substituting everything in. So 2 log 4 and bracket. Oh, and I'm gonna need to I'm gonna insert a bracket there. Okay, plus 3 log 6. Okay, and then I end the bracket for the first one, and then divided by, okay, bracket. And I'm just gonna put 0.5 for the half, and then log 4. and then minus 2 log 6 bracket bracket. Okay, so I've got negative, and then what do I want? 2 decimal places, so negative 2.82. Negative 2.82 is what x is equal to. Okay, so verify by graphing. So this is what I'm talking about, how you would put this into your y1. Okay, so let's clear this. We'll probably have to adjust, well, maybe adjust our windows. So we've got 4 raised to the power of 0.5 x minus 2, and then 6 raised to the power of 2x plus 3, and I'm pretty sure that it should graph that without, okay, so yeah, my window, oops, it's not done yet. Okay, so my x max is to 100, but I know that my solution's negative 2.8, so I'm gonna go like negative 5, positive 5, and see what that gets me. Okay, so there's one, and then the other one goes up like that. So I'm going to have to adjust my window. So I'm gonna go my y min, oopsies. So x min was, what was it, negative 5. And then my y min, I'm gonna go negative 5, positive 5, and see if that helps now. Okay, so I get a better, okay, so now, let's see if this worked. 5, intersect, oh dang it, quit, that was my bad. Graph, intersect, number 5, 1, 2, 3, and then does it give us, so what did I have, 2.82, see, I think that it, because that's not the same, so I'm gonna go to my window, and I'm pretty sure I have to put brackets around, so I'm gonna insert bracket, so that this is all being raised, okay? I kind of think I remember that you need to do that. And let's try this again. Okay, so there's our exponential growth. That makes more sense. And there's our other exponential growth. Okay, and so we know that it's going to intersect at negative 2.83, so we should be able to just do the zoom trace. 1, 2, 3. And hopefully it's equal to, there's my negative 2.82. Excellent. So done that. Write down the feature the calculator used and provide a sketch to support your answer. So we did y1 was 4 1/2 x minus 2. y2 was 6 2x plus 3. And then we can just show, so we had this, and we had it going like this, and then we had it going like this, and that right there was the negative 2.82. And then of course we always label our graphs. Okay, so then this one, so in order to figure out which one, you can just trace, or can I figure it out? Let's see. If I go to my y equals and then I just delete this one and graph it, so then the one that's left is the 4, base 4, so which this is this one right here, 4 1/2 x minus 2, and then that means this one is 6 2x plus 3. All right, so now we've got part C, show the solution. So this right here can be written like that. So all we're doing is using our log laws to rearrange it. So starting off with the top, so x is equal to, so I would put this 2 up to the 4 and this 3 up to the 6. Okay, so I would use my power laws and I would communicate that I was doing that there. So it's gonna be log 4 squared plus log 6 cubed, and then log 4 1/2 minus 2 log, 6 2. Okay, so now since I'm adding these, okay, those are going to get multiplied. So I'd have log of, so it's going to be 16 times, I'm just going to leave it like this for now. Okay, and then on the bottom, it's going to be, so this is being subtracted here, so log of 4 to the 1/2 over 6 squared, okay? And now we've got, I guess we do just need to like evaluate these, okay? Do I have anything? Let's see. Okay, so let's just put those in there. So 4 squared, 4 squared, quit. Oh no, quit. Clear. So 16 times, I think that's 216 is 3,000 log 3,456. Okay, and then we've got, so the square root of 4, well that's 2. So 2 divided by 36, right there. 2 divided by 36, which is the same as 1 over 18, okay? And so then we've got log of 1 over 18, okay? Which, if you notice here, it's 18, and then look at that negative. So all I have to do here, I would use the power law. Okay, so the top stays the same. Okay, and then I would write log, so this is 18 to the power of -1, and then I would bring that out front. So that's negative 3,456 over log 18. There we go. That was what we wanted to be demonstrated. So now you can work on your assignment.